Hi, this is Tzvi Rosen, and today we're going to continue covering Chapter 2 of A.T.M. McDonald by looking at exact sequences and the Hom functor and how those two interact. And here's a quick outline. We'll start defining exact sequences with some examples, then we'll go into Hom and move on to some examples showing how the two interact. Okay, first up, we'll talk about exact sequences. So an exact sequence is if we have a sequence of A modules, so let Mi for I equals 1, etc., be a sequence of A modules with A module homomorphisms Fi mapping Mi to Mi plus 1. Okay, and I guess we could give this a set notation. Then the sequence given by having Fi here, Fi plus 1 here, and then as many arrows as you'd like going off in either direction, is called an exact sequence. If for all I, the kernel of Fi plus 1 is equal to the image of Fi. So you'll notice both of those in this example, or in this little snapshot of the exact sequence, are submodules of Mi plus 1. So if this module has image contained here inside of this module, then that is precisely what maps to 0 in this module. And that's so it's said to be exact at Mi plus 1. But if it's exact at each module, then it's called an exact sequence. Okay. A short exact sequence is a specific type where you have just 3 modules, and it looks something like this: 0 to M1 to M2 to M3 to 0. Okay, and what you can notice about this is that, so let's give these some names. We have F1, F2, F3, and F4. So first up, so F2 is injective, right? Because the image of F1 is just the zero element of M1. And since that's equal to the kernel of the next map, that means the kernel is equal to 0, which means the map is injective. Okay, F3 is surjective, okay, by the same type of reasoning, because the kernel of F4 has to be the entire module M3, okay, and that means that F3 must map onto that, because the image is going to be equal to the kernel. Furthermore, if you want to look at the co-kernel of F2, okay, so again, that's the quotient of M2 by the image of F2. So co-kernel of F2, that's going to be equal to M2 modulo, so we're saying it's the image of F2, but that's equal to the kernel of F3, so that's the same thing. Okay, and that just follows from standard isomorphism theorems. So short exact sequences are really important. They're kind of the building blocks for all long exact sequences, which we'll see in a moment. And the reason they're so important is you can think of them as showing how this central module, so the M2 in this case, splits up into M1, which is a substructure, and then M3, which is kind of a complementary quotient structure. And that's why you'll find this in a lot of areas of algebra, not just commutative algebra, but it's a really important building block for understanding the structure of modules. Okay, and let's show how you can reduce a long exact sequence into short exact sequences. So let's say you have something like M1, M2, 3, M4, M5. Okay, that should be enough. Okay, so how can I turn this into a collection of short exact sequences? So I want it to be just 3 non-zero modules with 0 on either side. Well, start here and take 0 to M1 and M2, and then instead of taking M3, because I want it to, see, this one is exact, which means that the map from M2 to M3 is not necessarily surjective, but its image is equal to the kernel of the following map. So instead, we'll want to take, instead of M3, we'll take the image of F2. Okay, this is F2. I might have changed my indexing at some point, but you'll forgive me. And that, obviously, since it's surjective, by definition, that will map onto 0. And then you can keep breaking it down this way. To extract the next chunk of this long exact sequence, so we want to have M3 in the middle, and to get something that injects into M3, we take a submodule of M3, and the natural submodule to take there is just the image of F2. Okay, so that's going to inject into M3 because it's a submodule, and we also know that the image of F2 is equal to the kernel of F3, so it makes sense that the next map should be F3. And so this would map to the image of F3 if we want it to be surjective. And that maps us to 0. And by the same token, each of these maps, each of these segments of the exact sequence can be extracted. So we choose which module we want to be focusing on, and then we take the submodule corresponding to the image of the previous map and map onto the image of the homomorphism in the subsequent map. And because the image of F4, since F4 is surjective, this is just going to be equal to M5. Okay, so we're able to turn this long exact sequence into 3 short exact sequences. Okay. And you can patch it together to go the other way. Here's an interesting proposition presented by Etienne MacDonald, which shows where a pair of short exact sequences in a commutative diagram leads to a construction of a natural long exact sequence. And it's presented here. So we have this pair of short exact sequences in the m's and the n's. And we're told that there's an exact sequence which starts up here, and it's in the specific submodule kernel of f prime, which is a submodule of m prime, and then maps to kernel of f, which is here, and then to kernel of f double prime, which is here, and then it snakes around, oops, and it goes to a submodule here, which is the co-kernel of f prime, and then into the co-kernel of f and the co-kernel of f double prime. Okay? And the maps that are associated to each of these are pretty natural. So you have kind of u bar, which is just the restriction of u to the submodule of m prime, and similarly v bar here. And down here you get u prime bar and v prime bar. So those are natural maps. The only really interesting map is this one, which is called a boundary homomorphism. Okay. And the challenge of proving this proposition amounts to something called diagram chasing, which is basically showing that because the diagram commutes, you can find elements corresponding to different elements wherever you need, so that the resulting sequence is exact. And maybe we can just show one step of that. So if we have u bar, so we want to show that u bar is injective in order for the sequence to be exact at kernel of f prime. So how do we show that u bar is injective? Well, let's suppose we have an element which maps to 0 under u bar. Okay, so u bar of x equals 0. Well, that means that u of x equals 0. And by injectivity of u, that means that x equals 0. So u injective. So that wasn't particularly hard. That one is kind of easy, so we'll try another stage of this. So let's show that the sequence is exact at kernel of f. So to show that it's exact at kernel of f, so let's label these maps. This is u bar and this is v bar. Again, that's just the restriction to the submodules. Then we want to show that kernel of v bar is equal to image of u bar. Okay, well, one direction of this is relatively simple. Because these are just restrictions of maps that are exact, so if we consider what happens to v bar of u bar applied to a certain element, that's going to be the same as if we applied the bigger map. And we know that that's 0 by exactness. So the image being contained in the kernel is not a hard direction. What remains is we want to show that the kernel of v bar is contained in the image of u bar. So if we have any element in the kernel of v bar, we need to find that it's in the image of u bar. So let's start by taking x in the kernel of v bar. That means that v bar of x, so first of all, it has to be inside of kernel of f, okay, just by virtue of the stage we're at in the sequence. That implies, first of all, that f of x is 0, but also that v bar of x is 0, which implies v of x is 0, of course. So the fact that v of x equals 0 means that it's not only in the kernel of v bar, it's in the kernel of v. And we know that that's equal to the image of u. So we have to have some y in m prime such that u of y is equal to x. Okay, but we don't know if this is in the kernel of f prime yet, right? This only works if y is in the kernel of f prime. So that's what we're going to show next. So we need y is in kernel of f prime. And in order to prove that, we'll use the commutativity of this diagram. So we have that u of y equals x, which is in the kernel of f, right? So we have, if we put y here, so if y were here, it would go to x over here. We know that's in the kernel of f, so it goes to 0 over here. So by commutativity, that means that if we go this route, it should also go to 0. But that means that f prime, so let's put it this way, commutativity implies that f of u of y, which is 0, should be equal to u prime of f prime of y. Okay, well, if u prime of f prime of y is 0, so what that means about f prime is that since u prime is injective, by virtue of exactness of the lower sequence, that tells us that f prime of y is 0, because that's the only preimage of 0, but that tells us it's in kernel of f prime, which is exactly what we needed. Okay, so that tells us that that the sequence is exact at kernel of f. Okay, and we'll just do one more of these, and that's in order to specify what this boundary homomorphism is. So what is the boundary homomorphism? Okay, so we want to be able to take something from kernel of f double prime and map it to something in co-kernel of f prime. We'll start by taking some x in kernel of f double prime. We want to be able to specify an element in the co-kernel of f prime using this. So what do we know about x? Well, if it's in the kernel of f double prime, that means that f double prime of x equals 0. So that's one thing. We also know that the upper sequence is exact, so that means that there exists y in M such that v of y equals x. Okay, well, now we can do some diagram chasing, follow where a given element goes in this complex. So if we have y over here, goes to x over here, which goes to 0 over here, so it should go the same this way. And furthermore, we know that the diagram commutes. So whatever y maps to is in the kernel of v prime. Okay, so that means that f of y is in the kernel of v prime. Okay. So now we have a f of y in the kernel of v prime, but we know by exactness of the lower sequence that that means that f of y is also in the image of u prime. Okay, so that means that there exists, so let's also note that u is injective. U is injective, sorry, u prime. Also u, but u prime certainly. U prime is injective. This implies that there must be a unique element mapping to f of y under u prime, such that u prime of z equals f of y. And so the boundary homomorphism is going to be defined as taking delta of x to be equal to z bar, where the bar indicates the image of z in the co-kernel. Okay. And there's a missing step here, which is to verify that no matter which element y in this module we chose, we would still end up with the same z-bar in the co-kernel. But that we'll leave for our problem session. Okay, now let's talk about additive functions on exact sequences. So we're going to define an additive function on modules. Okay, so let lambda be a function on some class C of modules to z satisfying the relation that if you have an exact sequence, let's make it a short exact sequence. Zero to A to B to C to 0. Lambda of A plus lambda of C is equal to lambda of B. Then lambda is called additive, an additive function. Okay. And why would we care about additive functions on exact sequences? There's a really nice example from topology, and first we're going to have to define some modules associated to a polytope or a polyhedron, and then show how this additive function will give us a classic formula from geometry. We're going to define the vertices, edges, and two-dimensional faces of a polyhedron using the letters V, E, and F. And then we can take the module generated by those sets. So this will be Z, F, Z, E, and Z, V. Now the maps among these modules will work as follows. So if we have a face of our polyhedron, so for instance, something that looks like this, with vertices labeled something like this, then we'll give a natural orientation to the perimeter, so let's say clockwise. And then to map to the edges, to the module of edges, we just take each module, we take each edge with a sign corresponding to whether you're going from the smaller vertex to the larger vertex, it will be positive, and if it's the opposite, it'll be negative. So here we'll have E12 plus E23 plus E34 minus E14. Okay, because we start at vertex 4 and go to vertex 1, so it gets the negative sign. And then to go to the module of vertices, each edge maps to the second vertex minus the first vertex. So we have E12 maps to V2 minus V1 plus V3 minus V2 plus V3 minus V4 minus V4 minus V1. Okay. And as you can see, we have a lot of cancellation here. And sorry, I made a mistake here, which I could tell because I didn't have the right amount of cancellation. So this should be V4 minus V3. and then the v1s cancel because it's minus a minus over here, and the v3s cancel, and the v4s cancel, and we're left with 0. And it's not hard to show that, assuming we're dealing with a solid polyhedron, all faces solid, then this sequence will actually be exact at ZE. Unfortunately, it won't be quite exact if we enlarge it just by zeros. So we need to add in one copy of Z corresponding to kind of the solid, and then we can take this sequence. So solid passes to faces, passes to edges, passes to vertices, and then we also need a face corresponding to the empty set. So that'll get us another copy of Z, and this is an exact sequence. Okay, so let's borrow this. Oops. So taking this sequence, we can apply an additive function. And the additive function will simply be the rank of each module. So how many generators you need for each module. So lambda of m equals rank of m. And when I apply lambda to each of these, so taking lambda, so lambda equals, here it's 1, here it's the number of faces of your polyhedron, here it's the number of edges, here it's the number of vertices, here it's the, again, 1. And so I told you that in a short exact sequence, you need that the outer two add up to the inner one. But that translates into an alternating sum property. So in general, so for general exact sequences, you can just have an alternating sum, and that should add up to 0. Okay, where n goes through the set of indices. So for us, what does that mean? It means we have 1 minus f plus e minus v plus 1 equals 0. And rearranging, this means that v minus e plus f equals 2. And this is familiar as the formula for the Euler characteristic of a convex polyhedron. So this is the Euler characteristic. Okay, and we get that just from applying this rule of additive functions to this exact sequence of modules associated to the convex polyhedron. Okay, so I really like that example. I saw it on Math Stack Exchange looking for some friendly examples, and was written by Sean Alt. Okay, so that's it for exact sequences until we apply Hom to them. But first, let's look at Hom. So Hom is something, so given m and n A modules, okay, where A is a ring, Hom of mn is equal to the set of module or A module homomorphisms from m to n. If there's ever any doubt about what ring we're considering these as modules over, you might put an A here to let us know that these are A module homomorphisms. But in general, it's not going to be super ambiguous because you'll know what ring these are defined over in most cases. And this actually has the structure of an A module. Okay. So let's confirm that that's the case. We need that it's an abelian group and it has A multiplication. So if we have, for instance, f from m to n and g from m to n, so n is an abelian group because it's a module. So we can just define f minus g from m to n given just as it'll map x to f of x minus g of x. Okay, and plainly this works. You can get additive inverses here because you can take f and you can take minus f. So this is an abelian group. And in terms of multiplication by a, so if given f from m to n and a and a, you can define af as mapping m to n, just sending x to af of x. Okay, and that's perfectly well defined, again, because we have that n is an A module. Okay, but more so than just having this one structure, Hom of mn being a module, we actually have that this is a functor from the category of modules to itself. In other words, so if I can apply this to all objects in the category, so we have A mod is the category of all A modules. Okay, and how does Hom m dot act on this? So on the objects, so it'll take n and it'll map it to the A module given by Hom of mn. Okay, and on morphisms, if you have a map f from we're already using m, from n to p, and this is assuming this is of course an A module homomorphism, then we can map this to Hom of mn to Hom of mp by taking any morphism here, any homomorphism here, let's make it G, and then just post-composing it with F. So if you do G, which maps M to N, and then you do F, which maps N to P, now you have a map from M to P. Okay? So this is how the functor acts on the objects and morphisms of this category. And it's, you can tell that since n mapping to p becomes Hom mn mapping to Hom mp, it's a covariant functor. It doesn't change the direction of the arrow. Okay, and obviously there are properties you have to check here that it works nicely with composition and the identity morphism, but that's not hard to do. On the other hand, if we have Hom dot n, this is the this is also a functor from A modules to itself. So functor from A modules to itself. And this functor is contravariant. So let's see how it acts. On objects, it's going to take m and map it to Hom mn. And on morphisms, it's going to take a map from M to P, and it's going to map it to a morphism from the homomorphisms of P to N to the homomorphisms of M to N. And how does this work? Well, if we have a map here, that gets sent to a map that's precomposed with f. So first you do f to send m to p, and then you do g. Okay? And so since the arrow switches direction, now instead of m to p, you have p to m, this is called a contravariant functor. And again, you have to check that the properties of functors are satisfied, but indeed they are. Okay, now we are going to relate this functor business to the exact sequences that we've been speaking about so far. And we're going to define a left exact functor. So for covariant functors, a left exact functor is one which takes this sequence and when I apply the functor, I get 0 to fm prime to f of m to f of m double prime is exact. So let's be a little clear. So if this is exact, then this is exact. But you'll notice that I left off the last 0 because I only get that the left part of this is exact. So another way of describing this is it maps kernels to kernels. Okay. Similarly, if we have 0 to m prime to m double prime to 0 being exact, and now we have a contravariant functor g, so this is like the second example we spoke about where the arrows switch direction, then for a left exact functor, a left exact contravariant functor, we're going to have the following. 0 to g of m double prime to g of m to g of m prime is exact, but again, we leave off that last 0. Okay, and here you can think of this as mapping co-kernels to kernels. Okay. Now let's see some explicit computations, get our hands dirty. Here we're just going to compute some Hom modules. So let's think about what the homomorphisms from the Z-module homomorphisms, and we can be a little explicit about that here. Z-module homomorphisms from Z to Z look like. Well, whatever the homomorphism is, let's take f to be some homomorphism. We know that f of 0 is always going to be equal to 0. How about f of 1? Well, this could actually change. So it's going to be some integer. But then, because this is a Z-module homomorphism, whenever I have f of k, I can write this as k times f of 1, which means that this is kn. So the value of f of 1 determines the homomorphism. So this implies that Hom z over z is isomorphic as an A module, as a Z module to Z. Okay, and in fact, given any ring, the homomorphisms from A to itself will always be isomorphic to A. Okay? Let's consider homomorphisms from Z2 to Q. Okay, and this also again considering as Z modules. Well, this is going to be hard to do because so we only have 2 elements of this module, right? So there's the 0 element and the 1 element. So f of 0 will obviously be 0, but no matter what f of 1 is, I'm going to have to face the reality that f of 1 plus f of 1 should be equal to 2f of 1, which will be equal to f of 2, but 2 is congruent to 0 in this module, so this has to be equal to 0. So that means that f of 1 itself must be 0. So this will be equivalent isomorphic to the 0 module. So Hom z of z2 q will be isomorphic to 0 module. So with Hom q to z, we're going to have some difficulty as well, because if we want to map 1 over n to anything, we need this to satisfy the identity that nf of 1 over n is equal to f of 1. But this is going to be some fixed integer m, whereas this has to be true for any n. Okay, but that means that any integer is going to be divisible, a divisor of this integer m, which implies that f of 1 over n must be 0, right? Because that's impossible. But that implies that f of 1 is 0, so f must just be identically 0. So Hom q z, and again this is as a z module, will automatically be 0. Okay, so we had one non-zero Hom module and two zero Hom modules. Okay, so we spoke about how these are left exact functors, how Hom is actually, I didn't actually say that. So we define left exact functors, and both of these versions of Hom are left exact functors. So they're going to respect the exactness of these sequences, but they're not going to be right exact. So on that last stage where you're looking at the surjection onto that final module, you're not going to have exactness. And here's an example of that. So let's consider taking the sequence z maps to z maps to z mod nz. Okay, in order for this to be exact, we're going to be multiplying by n here. So 1 gets sent to n, and that gets sent to 0 because you're quotienting out by multiples of n. Okay, so this is an exact sequence. This is nice and exact. Now look at what happens when we apply the Hom functor to this. So obviously Hom of 0 is 0. Hom zn, we use this abbreviation to save time. And then we get Hom znz to Hom zn, and then zn again, because we had that over here, to 0. So the sequence is exact. Well, first of all, what are each of these modules? Hom zn to z, well, we know, we did a similar example with z2 mapping to q, but any element that has torsion, meaning if you add it to itself enough times, it'll be 0, that can only map to 0. So this has to be the 0 module. And the same is obviously true here. Whereas here we have just a copy of Zn. As we showed, well, that was A homomorphisms from A to itself. So this is a bit different. But the Z module homomorphisms from Zn to Zn is given by, well, it's not necessarily Zn. No, I think it's, yeah, isomorphic to Zn. So we have exactness at the first step and exactness at the second step, because the image of the prior map is 0, right? Because it's just 0 mapping to 0, and the kernel, again, this is just what's mapping to 0. Well, it's still 0. But then when I get here, Zn, so the kernel of the map, because it's mapping to 0 now, has to be the whole thing. So if I write G here and F here, so the kernel of G will be equal to Zn, but the image of F is just equal to 0. So this breaks exactness. This shows why we just consider it left exact, but not right exact. Okay. On the other hand, if we're looking at the functor which has z in the second factor, okay, this is a contravariant functor. Now we can look at a different sequence. So we're going to take 0 mapping to z, which maps injectively into q, the rationals. And then you can take the quotient module of q by its submodule, the integers. You can think of this as numbers with fractional part, numbers with integer part 0 and just fractional part. This is an exact sequence. But now what happens when we apply this functor? So we get 0 maps to, okay, and again, this is a contravariant functor, so we're going to have this one come first. Hom q mod z to z maps to hom qz maps to hom zz maps to 0. And using the same reasoning as we did in the previous examples, any rational number which is when we're quotienting out by the integers, if you multiply it by its denominator, it's going to be 0. So that means the whole map has to just go to 0. So this is going to be the 0 module. Similarly for maps from q to z, right? We showed earlier that that has to be 0, whereas maps from z to itself, that's going to be the integers. So by the same reasoning as before, we have that the image of f is just 0, but the kernel of g is z, which means that this sequence is not right exact. Okay? We only have exactness at these phases, but we don't have the exactness in that last step. Okay, so hopefully that gives you a nice flavor for exact sequences and for Hom and what Hom does, and how as a functor, Hom is left exact but not right exact. Okay, I'll see you next lecture. We'll talk about tensor, the tensor product, which as an explicit construction is a really interesting object, but also has functorial properties that relate it very closely to Hom. And we'll see that next time. Thank you.